Okay, so we see a pattern in all these derivatives right here. Help me find what this pattern is just in general. If I have an x raised to any power, what am I actually doing? How did you get these numbers down here at the bottom? What did you do with this x to the n power? Okay, so I'm going to drop the n down in front. I totally agree. And then lower the exponent by 1. And that'll work every time you have something raised to a power. It's pretty nice, isn't it? It's good no one's mad at me. Usually people get mad at me for this because you guys have been working it out that whole long way. And
no, I'm probably going to forget this.
You won't. I promise you won't forget this. Oh, good question. We'll get there. And why are we just not learning this better way? Is because we appreciate the better way and we see what we're actually doing, what this shortcut is actually for. All right, so if I have x to the 6th and I'm wanting to take f prime of x, absolutely, we just drop the 6 down in front and then lower the exponent by 1. That is a lot quicker, isn't it?
I love that. This is great.
Oh. Chain rule. We're going to do rules for the next 2 weeks in here, differentiation rules. All right, x to the 1,000th power. Can you imagine doing that the old way? X plus h to the 1,000th power minus x.
No! Stop.
But everything in there would cancel out all the way down to just dropping the 1,000 down in front. So 999. That's pretty quick. I mean, one step. Think so? All right, what if I give you y is equal to t to the 4th and I ask for dy over dt? Yeah, that's just the Leibniz notation of derivatives. Yeah, it's the same thing. All right, what if Leibniz? He's kind of the boastful guy that came up with calculus. He came up with calculus, and he's like, "Hey, check this out! I'm able to do all this work." And then Newton pulls it off the shelf and is like, "Yeah, I wrote this a long time ago." Was it good? Leibniz. All right, what if I say d over dr of r cubed? Awesome. Round 2. Leibniz. All right, let me see if I can throw a wrench in this. This is going too well. Okay, so make it look like a power function. It's a reciprocal function, but yeah, make it look like what it would be if it was a power function. Again, I've got to get it down to that form x raised to a power. And so if that happens, yeah. Good. All right, now what about f down here? So let's rewrite it first. Make it so we can use this new rule that we have. Yes, you must go down. You're going down 1 unit. So what that allows us to do is to actually rewrite our power rule a little bit better. So good question. If I subtracted 1 from that 1/2, 1/2 minus 1 gave me negative 1/2. I'm always just subtracting 1 from that exponent. So what we can do is we can expand our power rule now, and we can say if n is any real number, as long as we're not in the imaginary plane, and we have any real number, I am able to just drop this n down in front and then lower the exponent by 1. And that'll work every time. The power rule said it had to be a positive integer. I'm saying we can expand that out now, and we can make it so our power rule says that it can just be any real number. This is the power rule. Yeah. I'm not going to revise it anymore. I remember. That's all I got for you. Oh, you want to do more examples? All right. We can do more examples. Let's do G and H here. Do what? Yeah, same thing, except for it says real. Why are we doing more examples? This is example 1G. Yeah. So I need to rewrite this. All right? I can't have a 1 over. I can't have that division in there yet. That's coming next week. Okay. So rewrite this guy as x to the negative second. I agree. Negative third. Subtract 1 off that. So again, the negative 2 drops to the front. And then I'm just going to lower this exponent by 1. Yes. I'm wanting to bring this to the top, and whenever it switches sides, I just throw a negative on it. What about the cube root of x squared? X squared times 1/3, yeah. Because taking something to the third power is the same as taking the cube root of it. We're on the same page there. And then something with the power to a power, I multiply their exponents. Now, common mistake right here. A lot of students will say, oh, sweet, that derivative wasn't too hard. Nope, that's what y is equal to, all right? I'm wanting a dy over dx here. Good. We have to do some calculus on it now. So the 2/3 drops to the front. And I lower the exponent by 1. Negative 1/3. So everybody's good? Is there? I don't know. I think we just need to practice it.
And I don't even know if this is the second.
Oh, we have another example. All right. We can keep going. I'm good whenever you guys are. It's 15 minutes in the class. All right, so let's try to redo some of our applications of derivatives using our new method, our new power rule. X to the what? Okay. I like fractions better. You guys want to do decimal? I don't care. 1 1/2. I like 3/2. Because this is to the first power. If I get rid of that, that's the 1/2, 3/2. So what would the derivative of that be?
Yeah.
I agree. 3/2 x to the 1/2 power. Now, I'm just going to warn you, the book might simplify this. I'm not going to be real big on this yet, but you're going to see the book simplify this more and more to where they take this x to the 1/2 power and they go ahead and throw it back inside there. It's not a big deal. I wouldn't count this wrong yet. All right, but you might want to start simplifying more. You'll see why you will want to simplify it more with the stuff we have to do. Okay, so now remember this is going to be the slope of my tangent line because I took the derivative, which was a lot easier again than the x plus h minus f of x all over h. So now if this is my slope, how do I find this slope at the point 1, 1? Plug it into y equals mx plus b. Okay, so I'm going to use y equals mx plus b. I agree. What's my b? Oh, what's my slope? So I just plug in. You guys are being confusing. All right, so why don't I'm just going to work this slope out separately over here. So I'm going to take this one right here. That's my x. And so I get 3/2 for my slope. I'm going to go ahead and plug in that slope right here. Now I think it's going to be easier to plug in x and y. If you're plugging in 1 here at the same time that you're plugging in 1 in for x and y, I think that's going to get hard. Because I'm finding the slope at this point right here. I'm finding the slope at x equals 1. So now, well, there's a couple ways you can do it. You have a slope now. You have a point. You can do point-slope form. Or you guys tend to like to take this 1, 1 right here and put it in for x and y, and then just solve for b. You'll use the one the first time to find the slope of the tangent line, because this thing doesn't have a constant slope. The slope's changing as it goes throughout the function. But at the point 1, which happens to be 1, 1, if I was to put that in, the slope of that tangent line there is 3/2. Okay. Now that I have the slope at that point, I can plug in that point in for x and y. It is. And I get my b is 1/2. Good. Negative 1/2. So now I've got my slope, I've got my y-intercept, I'm ready to wrap this up. Y equals 3/2 x minus 1/2. So that problem got a little quicker. Okay. What if they throw a constant in front of it? All right, constant multiple rule says that if I'm taking the derivative and I have a constant in front of my function, I can pull that constant out in front of my derivative and just take the derivative of that function. Yeah. So, and I can do this because of limits. Remember, I can always pull my constant out in front of that limit and then just take the limit of the function of x. And so remember that all this derivative is the limit as h approaches 0 of my difference quotient. So that's what allows me to do this. Okay, so let's try this. Okay, so the 3, you're right, the 3 can pull out in front of my derivative here to where I can just take the derivative of that x to the 4th. Oh, let's do this step by step so everybody's with me. So if I take the derivative of x to the 4th power, what does that give me? 4x to the 3rd. And I can go ahead and combine these. Go ahead and multiply my coefficients through. You guys see a better way of working this? Yeah. Just do 4 times 3, and that's 12, and then lower the exponent by 1 still. And that's going to work every time. You won't. You won't. Ooh. This is on the quiz too. So what's going on? -1. Okay, I agree. Okay. -1 times 1 times 1. Okay, so we brought the -1 to the front. And we dropped this 1 down to the front, and we lowered the exponent by 1. That gave me x to the 0. So I have a -1 times 1. X to the 0 is 1. -1 times 1 times 1 is -1. Interesting.
Franklin, if you come to the office, please, Mike, Franklin.
Maybe there's another one that's going to pop up on here. Oh. Well, what if I'm adding 2 functions together? Yeah. Because remember the limit of the sum was the sum of the limits, right? And so since the derivative is just a limit, I can erase, yeah. I can just split up that derivative and take the derivative of each function of x. And that's going to be true whether I am adding or subtracting. And we might finish this in one day. All right, ready? I think you are.
So I'm just going to separate all of those.
Separate all of those?
Separate it.
Okay, so first question I have, so I can split up this derivative, and I'm just taking the derivative of each term of this polynomial going down, okay? How do you guys feel about that constant multiple rule? Do you want me to go ahead and bring the 12 out in front of the d over dx, or do you just want to do the 5 times 12? Oh, yeah? Okay. You're going to see me work this shorter and shorter, though, all right? Well, no, I'm just saying in front of each one. So I can take the derivative of each guy here. You know, obviously we're not going to do this every time. So I'm going to skip this next step, bringing the 12 out in front. That constant multiple rule, it's nice and it shows you why it works, but it's going to work the same. So you and your pod buddies, you guys go ahead and take the derivative of that whole thing and then see if you match up. I don't know. So notice I didn't bring like this 4. Ooh.
You did bring it somewhere.
Notice I didn't bring this 4 out in front, all right? So we're going to get maybe quicker and quicker ways. And you probably won't see me write d over dx in front of every term anymore. I kind of understand that this d over dx is going to distribute all the way through, and I'm going to take the limit or the derivative of each term in a polynomial. Okay, so we're clear on that. Okay. Well, let's look at it. I can pull this 6 out in front, right? And I get negative 6 times the derivative of x. And you guys told me earlier the derivative of x is just 1, so it would still be negative 6. So we got to find the points on the curve where the tangent line is horizontal. Well, I'm probably going to need a derivative, right? What's my derivative? Was 0. All right, 4 goes to 0. What can you tell me about a tangent line that's horizontal? Its slope is 0, right? It's a horizontal tangent line. Its slope is 0. Isn't this the slope anywhere on this line? So I'm interested where my derivative is equal to 0, where my slope, the slope of my tangent line is equal to 0. How do I solve this for x?
Well, you factor out that 4x.
Okay. Factor out of 4x? Okay. 0 product factories. Factory. 0 product. What are they called? It does. Anything will factor, but I don't think we need to. So x is, you said plus or minus square root of 3? I agree. Well, did we answer the question?
I mean, you just have to say that
All right, what's the points? So I'm willing to bet I need to set this up and find each one. All right. All right, so this table over here, you guys take square root of 3. I'm going to give these two tables negative square root of 3. I'll take the 0. Oh, well, yeah, which one do we plug it into? What happens if I plug it into this one? Everything's going to be 0, right? So that doesn't make much sense. I'm wanting help in finding the tangent lines that are horizontal on this function. So I'm going to plug it back into this function. So I'll do 0. You guys do the others. Both are negative 5? Okay, it is. It is an even function. So you plug in one, you get the other. I mean, we might finish today. We're going good. Okay, so I've got this particle that is moving around, and this is this position function right here. Can I find the acceleration from that?
That's the second derivative.
The second derivative.
There's derivative is velocity.
Oh, hold on. So I'm going to take the derivative of this s up here. Derivative of that s is going to tell me what?
So derivative is going to tell you velocity.
Well, we have a particle and mover. This is just the rate of change, right? It's the rate of change, but we're not talking about a graph this time. We're talking about a physics problem. We're talking about something moving. So if I'm saying how fast something's changing as it moves, that's its velocity, right? So yeah, first derivative will be the velocity. So what is the velocity of this? I agree. Any questions on that? And so I could do whatever I needed to with the velocity. He wants me to take it a step further, and you guys said that the second derivative, or the derivative of the velocity, is going to be my acceleration. Okay, remember velocity or acceleration is just how fast my velocity is changing. It's how fast the velocity of a high school student is pulling out of the parking lot. Right? We call that acceleration. So what is this equation going to be? Good.
That should be it. That's the velocity.
Works for me. Questions on that? Okay. Took the first derivative, and that gave me velocity. And then I just did it again, and that gives me acceleration. If I did that again, it would just tell me how fast the acceleration is changing, which is weird. I don't know what that is. That would be a question for your physics teacher.
No, we're doing the exponential. You have more slides for us?
I know.
You don't?
I can go check.
Okay. Well, I've already reminded you.
You can. Okay, so this is how I get Euler's Z. If you remember, we typed in something really close to 0. Anyway, it gives us 1 right here. All right? And whenever I take the derivative of it, the way that we graphed it was we went through here and we went through 1 and then 2.7. And it looks something like this. Now, have you guys done your homework from the last section? Because we took the derivative of e to the x, and what did you guys find out? It is actually just e to the x. How nice is that? Meaning that if I was to take the slope of the tangent line at all of these points, if I take the slope of the tangent line right here at this x, it is 2.7. If I take the slope of the tangent line at this x, it is exactly 1. If I take the slope of the tangent line here, it lands on this exact same line. To where if I take the slope, if I change all of these y values that are on this blue line to the slope, I get my derivative to lie right on top of it. That's pretty cool, isn't it? Yeah. So we use Euler's E a lot in calculus. I already said that. All right. Okay, so I agree. Again, I'm taking the derivative of this. I'm taking the derivative of each term. Okay, even though this is not a polynomial anymore, Euler's E is going to be easy to mix in with these. Okay, so I take the derivative of e to the x. Well, that's just going to be e to the x. And I take the derivative of negative x, and that's minus 1. And that'd be my first derivative. I agree. Second derivative, I'm going to take the derivative of e to the x, which is just e to the x. I take the derivative of negative 1 is 0. What would be the third derivative? What's the fourth? The fifth. Exactly. I just quits right there. All right. Oh, it's not. Yeah, let's not. All right. There you go.